All right, these are the 14.3 notes on the ideal gas law. So the ideal gas law includes four variables now. It's pressure, volume, temperature, and the amount of gas, so N. This is the only equation of the ones you're working with that deals with an amount of gas. So N is going to be moles of gas, and we plug that in right here. So the ideal gas law is this equation right here. Pressure times volume equals moles of gas times R. R is called the ideal gas constant. The ideal gas constant, and I'll get to that in a second, it's just a number that you plug in. And then T is temperature. It shows how the ideal gas constant is derived and how they come about with that number. What you really need to focus on is this right down here. This is what you plug in for R in the equation. So it's 8.31 and then liters, kilopascals over kelvins, mole. Those are just the units and they will cancel out when you do the problem. But 8.31 is the number that you put in for R. So I'm going to look at a couple of practice problems. The first one says at 307 Kelvin, the pressure inside a nitrogen-filled tennis ball with a volume of 0.148 liters is 212 kilopascals. How many moles of nitrogen gas are in the tennis ball? All right, so we're using the ideal gas law, so it's going to be PV equals nRT. Now, when you're using this equation, the units are very important. So pressure, I'll just make a note here, the pressure has to be in kPa, the volume has to be in liters, N has to be in moles, R is always that ideal gas constant, so it's always 8.31 liters, kilopascals, kelvins, moles. But 8.31 is the number you put in. And then temperature always has to be, just like the other ones, it has to be in the Kelvin scale. So it's very important that if you're not given those units in the problem, you have to make a conversion before you plug them in. All right, so in this equation, we want to find how many moles of nitrogen. That means we're going to solve this equation for N. So if we rearrange this, to solve for N, you want to isolate that. So you're going to divide both sides by R and T. So it works out where N is equal to PV over RT. Now we can just take the numbers from the problem and plug everything in. So the pressure is 212 kPa. The volume is 0.148 liters. And in this problem, everything is in the correct units already, so we can just plug them right into the equation. R, that's our ideal gas constant, 8.31. You plug in all those units for R, because they'll cancel out. And then T is the temperature, and that's in Kelvin, 307 Kelvin. Now the units work out: kilopascals cancel, liters cancel, kelvins cancel, and your answer is going to be in moles. And for this, I get N is 0.012 moles. Now, just so we're clear, the way I got from here to there, you're always going to divide, in this equation, you're always going to divide to isolate the variable that you're looking for. In this case, we want to solve for N, so it's multiplied by RT. So you have to divide both sides by RT. On this side, they cancel out, N is left over. So that's the equation right there for N. So that's how I got from here down to there. All right, so in the next practice problem, 35 grams of carbon dioxide are in a 2,800 milliliter container at 50 degrees Celsius. What is the pressure in the container? So we want to find pressure. We're given mass we're given a volume, and you're given a temperature. Now, the issue here is that all these are in the wrong units. So we have to make conversions before you plug in numbers into the equation. So N, start with that, that has to be in moles. So we have 35 grams are given, so we have to make a mole conversion. Carbon dioxide is CO2. So it's just a one-step mole conversion. The molar mass of CO2 goes on the bottom here. You know, carbon is 12, oxygen is 16. So 2 oxygens make it 32 plus 12. So the molar mass is 44 grams. So 35 divided by 44, that's 0.79 moles. Okay, so that's N. The volume has to be in liters. So 2,800 milliliters, we make that conversion. There's 1,000 milliliters in a liter, so that becomes 2.8 liters. And then 50 degrees Celsius, so it has to be in the Kelvin scale. So we just have to add 273 to that, so that's going to be 323 Kelvin. Okay, now we have the numbers already. Now we can plug it into the equation. So ideal gas law again, PV equals nRT. We're solving for pressure, so we want to divide by volume to get pressure isolated all by itself. So pressure is equal to nRT divided by V. Now you can plug the numbers in that we have. N is 0.79 moles. R is that same gas constant, 8.31. And you include all the units with the gas constant. T, 323 Kelvin. And we divide that all by the volume, 2.8 liters. Okay, when I do the math, I get the pressure is 757. Now for the units, most of the units cancel out except for kPa. So the units of pressure are kPa. And that's the answer, 757 kPa. Now with this equation, just remember, you have to know R. Remember that, 8.31. You'll use that every time you see R. And just remember that the units are very important in this equation. And if they're not in the proper units, then you have to make those conversions before we plug them in. All right, so that's the end of the notes for section 14.3.